Future Foundation, we would like to thank our warmest welcome to all esteemed delegates, faculties, members, researchers, students, and attendees of these events. Thank you. So, dear distinguished participants, so today joining with us today, we would like to introduce the distinguished guests and delegates. Firstly, we would like to warmly welcome our speaker today, Professor Yann LeCun, Vice President and Chief AI Scientist at Meta, Silver Professor at New York University. So please. Yeah. Okay. Please stand up and okay, thank you. Okay. So, and two invited panelists, Dr. Nguyễn Xuân Phong, Chief AI Officer, FPT Software. Professor Hồ Tú Bảo, Director of Data Science Lab at Vietnam Institute for Advanced Study in Mathematics, Professor Emeritus of Japan Advanced Institute of Science and Technology in Japan. So we would like to introduce from VNU, from VN Future Foundation, Dr. Phạm Văn Luân, Executive Secretary. And from Vietnam National University, Hanoi, Associate Professor Phạm Bảo Sơn, Vice Director. And from VNU University of Social Science and Humanities, Professor Hoàng Anh Tuấn, Rector. From VNU University of Science, Professor Vũ Hoàng Linh, Rector. And Associate Professor Trần Quốc Bình, Vice Rector. And Associate Professor Ngạt An Bang, Vice Rector. And joining with us today also, we have the leader from faculties and functional office of VNU University of Science. And especially the participants of researcher, students, scholars, and experts, as well as interested public attending the program in this hall, as well as on the live stream challenge. So now, we kindly invite Professor Vũ Hoàng Linh, Rector, to give the opening speech. So please.
Good morning, distinguished guests, esteemed colleagues, students, and friends. It is my great honor and privilege to welcome you all to this passion event hosted by VNU University of Science, Hanoi. Today, we are incredibly fortunate to have with us one of the most influential minds in artificial intelligence, Professor Yann LeCun, a trailblazer in the field and a true visionary. Professor LeCun, a recipient of the Turing Award, is known worldwide for his groundbreaking work on deep learning, neural networks, and their transformative impact on AI. His contributions have not only shaped the trajectory of modern AI research, but also opened new horizons for its application in solving real-world challenges. This talk is particularly meaningful as it takes place here at the VNU University of Science, a hub for innovation and a center of excellence in scientific research in Vietnam. We pride ourselves on fostering a vibrant academic community that is eager to engage with and contribute to global advancements in technology and science. Artificial intelligence, as we know, is revolutionizing every aspect of our lives, from healthcare and transportation to education and environmental sustainability. As we gather to hear from Professor LeCun about the future of AI, let us reflect on the opportunities and responsibilities that come with harnessing this powerful technology. I would like to take this opportunity to extend my heartfelt gratitude to Professor LeCun for visiting us and sharing his insights. I am confident that his talk will inspire all of us, faculty, researchers, and students alike, to push the boundaries of knowledge and contribute to the dynamic field of AI. We also express our thanks to the WinFuture Foundation for offering us a chance to host this event. Once again, thank you all for being here today. Let us now welcome Professor Yann LeCun to the stage. Thank you.
So thank you, Professor Ling. So our program today has two sections. In the first session, Professor Yann LeCun will give the keynote talk on the futures AI. And the second section is panel discussion and question answering with the participant of Professor Yann LeCun and three invited panelists. And I would like to invite Dr. Nguyễn Thị Minh Huyền, Head of Department of Informatics, Faculty of Mathematics, Mechanics, and Informatics to chair this talk. So please come in. Please come to the front of the stage. So.
Good morning, everyone. So it is my privilege to introduce our speaker for today talks on the future of AI. Can you please show the? Okay. Professor Yann LeCun is the Vice President and Chief AI Scientist at Meta and Senior Professor at New York University, affiliated with the current Institute of Mathematical Sciences and the Center for Data Science. He was a founding director of FAIR and of the New York University Center for Data Science. He received an engineering diploma from ESSEC Paris and a PhD from Sorbonne University. After a postdoc in Toronto, he joined AT&T Bell Labs in 1988 and AT&T Labs in 1996 as head of image processing research. He joined New York University as a professor in 2003 and Meta Facebook in 2013. His interests include AI, machine learning, computer perception, robotics, and computational neuroscience. He's recipient of the 2018 ACI Maturing Award with Geoffrey Hinton and Joshua Benjo for conceptual and engineering breakthroughs that have made deep learning, deep neural networks a critical component of computing. Professor LeCun is a member of the National Academy of Sciences, the National Academy of Engineering, the French Académie des Sciences. Professor LeCun's vision and insights continue to shape the future of AI, making him one of the most influential voices in this field. So today we are fortunate to hear directly from him about what lies ahead for this transformative technology. So please join me in warmly welcoming Professor Yann LeCun.
Thank you very much for the introduction. It's a real pleasure to be here. I have to start with a bit of a joke. My name here is spelled in one word, L-E-C-U-N, but the original spelling is in two words, L-E space C-U-N, and it sounds a bit Vietnamese. So when I joined Bell Labs in 1988, I was automatically signed up to a mailing list of employees of Vietnamese origin. And that was great. Okay, so let's see if we can switch to my slides. I'm not sure. Okay, but no, I just need to see my slides. J'ai partagé l'écran. Je suis en train de partager.
Et les slides, peut-être il faut partager l'entier.
Ça, c'est pas moi. Ça.
C'est déjà sur Zoom.
Oui, c'est sur Zoom.
New share.
C'est
Stop share.
your screen share. I'm sharing. I'm sharing.
Có được chờ một chút, chia sẻ lên Zoom em sẽ chuyển. Ok, chuyển đi.
All right. Okay. So I'm going to talk about how could machine reach human-level intelligence, but I tell you, we're going to have human-level intelligent machines before we have audio and video that actually works. Okay, so I think that's the big challenge, one of the big technological challenges and the big questions, scientific questions of the next decade or so, or maybe the next few decades, which is how do we really make progress towards intelligent machines? Some people have gotten the
Nga đã
impression
thiết lập các
that
vị trí ở phía tây các ngôi làng như
current AI systems already approach human intelligence. This is not true. Current AI systems are not nearly as intelligent as humans, certainly, but not even as intelligent as animals. This may sound surprising because we have AI systems that can manipulate language, that can even pass university exams, okay? But that doesn't mean they're intelligent. That means they're very good at retrieving knowledge and information. Okay, so how could we reach this? And I'm going to tell you a little bit about perhaps how we can get there. First, why do we need to build machines that are as intelligent as humans? And the reason is that there's going to be a future in which all of us will be walking around with intelligent AI assistant assisting us in our daily lives at all times. They're going to be in our smartphones or perhaps in our smart glasses, okay? We're going to be wearing smart glasses and we're going to be able to talk to our smart glasses. They're going to be able to display information in the screen. And inside of those glasses will be an AI assistant. Those AI assistants may be as smart as we are, maybe they will be smarter than humans. But what they will do is they will amplify our own intelligence, right? They're not going to replace us. They're going to be basically working for us. So it's going to be as if all of us will be the boss or the manager of a group of smart virtual people working for us, okay? This is the way the relationship between AI system and people is going to be. We're going to be their boss, basically. Thank you. So for this to work, though, we need those machines to basically have human-level intelligence, because that's the best way we know how to interact with intelligent systems. We are used to interacting with other humans. So we need the type of intelligence that all machines will have to be very much like human intelligence. So we need systems that understand the physical world, which current AI systems really are not capable of doing. We need systems that have persistent memory. We need systems that can plan complex action sequences. We need systems that can reason. And we need systems that are controllable and safe, so that they have some sort of proper behavior, if you want, some sort of moral behavior, if you want, okay? All of those things are impossible with current technology. Large language models that I'm sure many of you have played with and perhaps are using every day are incapable of any of this. They can do it a little bit, but not really very well. And so we have a big challenge, and I know there's a lot of students here in the room. You might get the false impression that AI is a solved problem, that perhaps there is no point studying AI anymore because, you know, we already have AI systems. It's not true. There's a lot of work to do, a lot of research to be done, a lot of scientific research to be done, in addition to a lot of technology to be developed. Okay, so the first thing that we need to think is, what are the essential characteristics that an AI system should have? And if you think about humans, when we are being asked a simple question, we can answer really quickly. If I ask you, does 2 plus 2 equal 4, you can say yes right away. Okay? And then there are questions that we have to think about to answer, even if the answer is very short. Which means that we have some internal process by which we kind of ruminate and we think about something before we produce an answer. What is this process? This process is not the same as propagating signals through a neural network, which is what large language models do, or current AI systems. Current AI systems produce their outputs mostly by just propagating signals through several layers of a neural net and then producing an output. It's true of systems that drive your car, or analyze medical images, or produce text, like large language models or chatbots. It's just forward propagation, and that's a very weak form of inference. The more powerful form of inference is one by which the system searches for an answer. It doesn't just compute an answer, but it searches for an answer that satisfies a number of criteria, okay? And so almost every problem that we're given, every problem that we solve in life, even those for which we don't consciously think of as requiring reasoning, we actually use this process of searching for an answer and then producing the answer. Okay, so this is a process by which the output of the system is not produced by propagating through a neural net, but it's produced by searching for an answer that optimizes a particular criterion. Let's call it a cost function, or let's call it an energy function. Here it's called an objective function. Okay, well, an objective function that measures to what extent an output is a good output for a particular input, and we search for an output that is compatible with this input, all right? That process is intrinsically more powerful than the one that consists in propagating a signal through a fixed number of layers in a neural net. So right away, we can tell that the current AI systems that we have do not have the right characteristics to be able to reason. They just don't. You might hear from optimistic people that, you know, the latest version of ChatGPT or whatever is capable of reasoning. it's true in a very restricted form, but in reality, it's just not true. So we need to build systems that are capable of doing this, right? Producing an output by optimization, essentially. And this is a very common concept. This is not a new concept at all in AI or even in statistics. The idea that you produce an output by optimizing. This is also the basis of classical AI. It's the basis of statistical inference. It's the basis of optimization, of operations research, of optimal control. A lot of areas of engineering and science are actually based on this idea of optimization. Okay, so there's nothing new there. But the difference between computing by propagating through a number of layers, just a simple computation, and producing an output by inference is the difference between what psychologists call system 1 and system 2. So system 1 is when you take an action without having to think about it. It's subconscious, right? So if you are an experienced driver, you can drive without really thinking about it. It's kind of subconscious, right? It's become second nature. System 2 is when you have to devote all your attention to a problem. Like you're solving a math problem or you are building something out of wood or whatever. You have to think, you have to plan, you have to devote your entire consciousness to it. Okay, that's system 2. Current AI systems are like system 1. What we need to build are AI systems that are capable of system 2. And this idea of inference by optimization, that's system 2. Okay, so let's talk a little bit about how this could be sort of conceptualized mathematically. And it can be conceptualized by what's called energy-based models. It's a concept I've been trying to popularize for a long time. So, in fact, I didn't realize this thing was annoying us. Let's see if I can move it out of the way. All right. Okay, so what's an energy-based model? Let's say that we have two variables, x and y. Let's assume x is an observed variable and y is a variable that we need to infer, that we need to compute, okay? And what we have is we've captured the dependency between x and y, but the relationship between x and y is not a function, in the sense that there is no single y that corresponds to an x. There might be multiple y's that correspond to a single x, okay? So there is a dependency between the two variables x and y, but we cannot reduce this dependency to a function. It's a more complex relation, okay? So let's take the example that we have here, where x and y are scalar variables, and the data points that we have are the black dots, okay? So the black dots are observed points of pairs x and y, okay? And there is obviously a dependency between those two variables, given where those black dots appear. What we need as an objective function to be able to infer the correct value of y from a value of x is a cost function, let's call it an energy function, that takes low values on the black dots and higher values outside. Okay? So think of it as a surface. What I've represented here with the colors are the lines of equal energy, if you want. Okay? And that surface takes low energy around the black dots and higher energy outside. So that if I give you a value of x, one of those red vertical lines, by searching along for a value of y that has low energy, you can tell me which values of y are compatible with that value of x, and that would be an optimization problem. Okay? Finding, for a given x, a set of values of y that minimize the energy f of x and y. Okay, so search for y check, which is the argument of f of xy that minimizes f of xy for a given x. So that would be inference. I haven't talked about learning yet. Okay, so now that I've told you about the basics of this, let me tell you why things like large language models are not of that type. So what is a large language model? A large language model is a system that is trained to basically produce the next word or the next token in a sequence, right? Take a sequence of symbols, it has to be a sequence of discrete objects. If they're not discrete, you have to discretize them. Okay, so words are discrete. There's only a finite number of words in a dictionary. So discretize that. And then train a big neural net to, train a big neural net I'm not controlling this, right? Thank you. So, okay. So I'm not sharing anymore. Okay, let me try. Okay, here we go. No, it's good. All right, let me take this out of the way. Okay, so a large language model is a system that takes a sequence of discrete objects, like words. They turn them into vectors that we call embeddings. Okay, there's a simple lookup table, basically, that turns the discrete objects, each word, into a vector. And then you train the system to predict the next item in the sequence. Okay, so give it a sequence of words, ask it to predict the next word. The details of how it's trained are irrelevant, but that's basically what it's trained to do. Once you've trained a system like this, you can have it generate a sequence of words by showing it a sequence of words, asking it to predict the next word, and then shifting that predicted word into the input. Okay, and then having it predict the second word, and then shifting that into the input, and the third word, etc. This is called autoregressive prediction. It's a very old concept, from statistics from the 1950s at least. So not a new idea at all. But what's new is the fact that when you train very large neural nets to do this on lots of data, there seems to be emerging properties, which is really the interesting part. Now, those systems, again, compute by forward propagating a signal through a neural net and just producing an output. There's a fixed amount of computation taking place per token produced in an LLM. And there is no process by which the LLM can reason or search for an answer. Okay, you have to add other characteristics to it. You can't use just an LLM for that. You have to modify it in many ways. And this is what a lot of people are working on at the moment. But it's still not perfect. And in fact, there is a series of papers that have appeared in the literature either from cognitive scientists who say, LLMs really don't do the same thing that animals and humans do, or from people coming from more classical AI saying those systems are not capable of reasoning at all. So there's a series of papers by this gentleman, Subaru Kambhampati. He's the former president of the AAAI, the Association for the Advancement of Artificial Intelligence. And he has a series of papers saying LLMs cannot plan, LLM still cannot plan. Even LLM that claim they can plan still cannot plan, etc. There's like he has 5 papers on this. There's also a tutorial on it that's interesting. Okay, so what do we need really? What kind of architecture should an AI system have if we want it to be able to reason? What it should have is what we have, which is an internal mental model of the world. We have a mental model of the world in our head that we manipulate every time we need to solve a problem. We can think about an action, and we can imagine what the result of taking an action will be. So if I take this bottle of water and I push it here, you probably know that it's going to fall, right? If I push it at the bottom, you can probably imagine that it's not going to fall. It's just going to slide. If I take this bottle, which is open, and I push it here, something bad is going to happen, right? It's going to flood my laptop, and the talk will be over. So we have this mental model of the world, and this is a very simple case, of course, that we all learned about this type of behavior when we were babies. But everything we do is related to our internal mental model of the world. Okay, so what is, we can call this a world model. What is a world model? A world model is something that says, here is the state of the world at time t, here is an action I imagine taking. Can I predict the state of the world at time t plus delta t, t plus 1, okay, after I've taken the action? That's a model of the world. State of the world, action, next state of the world. It could be also that the world is evolving by itself. You don't have to take any action for the world to change, okay? So the model of the world should include also some way of predicting what's going to happen in the world, even if you don't do anything. So that's a world model. Now, what can you do with a world model? If you have a world model, you can perceive the current state of the world, right? So observe the world through a perception system. That gives you an idea of the current state of the world. Of course, the current state of the world is not just what you can currently perceive. We perceive the content of this room right now, but we also have some good idea about the rest of the state of the world, right? We know what's going on outside in Hanoi. We know what's going on outside in Vietnam, in the rest of the world. You probably know in what state your house is or whatever, right? So your current perception has to be combined with the content of some memory that contains your idea, your current idea about the state of the world. Okay, so combine your initial idea of the current state of the world with your memory of what you think it is. Feed this to your world model together with an imagined action or sequence of actions you might want to take. And what your world model is doing is predicting the resulting state of the world. Now, if you want to accomplish a task, there's going to be a way to tell whether the task is accomplished. If I want this bottle to be on the left side of the lectern, I know I need to push it to the left side of the lectern, and I can determine whether it is indeed on the left side or not, okay? So there's going to be an objective mathematical function that has a scalar output that tells you the goal that you wanted to achieve has been achieved or not. Maybe it's a continuous value that takes value 0 if the goal is achieved, and then takes a larger value as the goal is, as the state that is achieved is more distant from the goal that you want. Okay? That's going to be our energy function. You know, I told you about energy-based models. That's going to be our energy function. It's the objective that determines whether a task has been accomplished or not. Okay, so now the process by which the system reasons and plans is that it's going to search for an action or a sequence of action, the yellow variable. Through optimization, it's going to search for a value of this action that minimizes the objective. Okay? So this assumes that we have basically 3 or 4 components in there. This assumes that we have a perception system. It assumes that we have a world model. It assumes also that we have an objective. And it assumes that we have some sort of hardwire mechanism in our system to basically optimize the objective with respect to the action. Now, if all of those modules are neural nets, let's say, they're all differentiable, which means we can do this optimization using gradient-based methods. Through gradient descent, we can figure out what action optimizes the objective. And again, I haven't said a single word about learning yet. This is all about inference. I'm assuming everything has been trained already. Now, generally, when we want to take an action, we actually want to take a sequence of actions. Okay, if I want to, fill this glass with water, I need to put the glass in the right place. I need to grab the bottle, pour some water in it. So it's a sequence of actions. But it's the same world model that I'm using. I'm just using it for multiple time steps, right? So this is kind of an unfolded version of what I just talked about, where you have the initial world state of first action that goes to the world model that predicts the next state of the world, and then the second action goes to the world model, predicts the second action, the second state, and then that goes into the task that measure the cost or the objective that measures whether the task has been accomplished. We can also feed the sequence of states to a set of costs that are guardrails that guarantee that the kind of actions that are taken are safe or secure. Okay? Obviously, I don't want to be taking this open bottle and wiggle it on top of my laptop because bad things may happen. You know, I don't want to be doing anything dangerous or whatever, right? So there are some guardrails that need to be applied when we do this, this inference, and that's basically the best way to make AI systems safe. You build them so that they optimize objective functions, and you build guardrails in those objective functions so that by construction, the system cannot actually take actions that would be dangerous according to its own internal world model. Now, this needs to be a little more complicated because the world is not deterministic. It's not entirely predictable either. And so the world model may be a deterministic function, but to make it non-deterministic, you had to feed it a set of latent variables. These are variables that you do not observe. They may be drawn for some distribution, or they may be swiped over a set, or chosen within a set. And they represent your uncertainty about the world. They are the hidden variables that, if you knew them, would allow you to predict what the world is going to do, but because you don't know them, you have to basically imagine what they could be in multiple scenarios. So I'm not going to go into the details of how you deal with this. That's planning under uncertainty. But the other thing you might want to do eventually, if you want to build a system of this type, is that you might want the planning to be hierarchical. Let me explain what I mean by that. So let's say I'm sitting at my office at NYU, at New York University, and I want to go to Paris. At a very abstract level, I know that I have to take two actions. I have to go to the airport and catch a plane. Okay? These are high-level actions. My low-level actions are muscle control, millisecond by millisecond, but I cannot plan my entire trip from New York to Paris in terms of millisecond by millisecond muscle control. I can plan it at a very abstract level, where the first action is go to the airport, second action is catch a plane. Okay, so now I have a sub-goal, which is go to the airport. How do I go to the airport? I'm in New York, so I can just go down on the street and hail a taxi. Okay, so now I have another sub-goal, go down on the street. How do I go down on the street? I have to walk to the elevator, push the button, take the elevator down, walk out the street. How do I go to the elevator? Well, I have to stand up from my chair, pick up my bag, open the door of my office, walk to the elevator. How do I actually stand up from my chair? Okay, that's my next sub-goal. Well, at some point, you know, the actions that you have to take are very low level. They come down to basically just muscle control. And below a certain level of abstraction, you don't need to plan. You can just do the action, okay, in a subconscious way. Because you've done it so many times, you don't need to think about it. So that's the way we reason. That's the way we plan. We have hierarchical representations of the state of the world at different levels of abstractions. We plan at a high level of abstraction for complex actions, and then that gives us sub-goals with which we plan. You're doing this right now. A lot of you are following studies at the university, right? Why are you doing this? Why are you studying for a degree? It's because you also, that's a sub-goal. You have an ultimate goal, which is succeed in life, maybe, or, you know, make a living, or maybe accomplish something, right? So that's why you're studying. And then that generates other sub-goals, you know, get a good grade on your next mathematics exam. That gives you another goal, you know, study, right, etc., right? So we do this all the time. We do hierarchical planning all the time. That's a characteristic of intelligent behavior. Now, let me tell you something. No AI system today is capable of doing any of this. Okay? We have no idea how to do this with AI systems. So if you want to start a graduate study, a PhD, or a research program, a master's in AI, this is a really good problem to attack because nobody knows how to do it. Don't work on large language models. Don't work on LLM. There's no point doing this. It's in the hands of industry. There's people with billions of dollars of resources working on it, making products out of it. It's completely boring. Work on this, or something like that. Okay, so I told you kind of, the basic setting of the problem, and I've actually written I wrote a paper almost like 2.5 years ago now on where I think AI research should go over the next 10 years. This was before a lot of people, heard about AI and ChatGPT and stuff like that, but my vision of this has not changed. So it's at this URL. It's not on archive, it's on open review, so you can make comments. And it's called A Path Towards Autonomous Machine Intelligence. And it's basically makes various proposals on how you could build a system of this type. I can't tell you that we built that system. We're building several parts of it, and I'll show you some examples. But that's what we're working towards. We have a big organization at Meta called FAIR, which means Fundamental AI Research. There's 500 scientists and engineers at FAIR. And that's basically our mission, building the next generation AI systems that may reach human-level intelligence. Okay, so I've sort of symbolized a little bit the architecture I just described to you in the form of kind of a virtual brain, if you want. But you have all those modules, the perception module, the memory, the world model, the cost function, or the objective function. The actor is the module that searches for the optimal action. And then there is this mysterious thing, the configurator at the top, which I'm not going to talk about. It's the thing that basically determines which goal you currently want to solve. So perhaps with an architecture of this type, we have a chance of actually fulfilling the requirements that I said AI systems should have and currently do not have. So the first problem we're going to have to face is how do we train a system to understand the world? How do we train this world model? And we have to use something called self-supervised learning. Self-supervised learning is what has revolutionized AI over the last 6 or 7 years. This is the way all the chatbots and everything are trained. Increasingly, computer vision systems also are trained with self-supervised learning. But another reason why we can convince ourselves that current AI systems are missing something big is that we have chatbots that can pass college exams or even the bar exam or something like that. But we don't have domestic robots. We don't have level 5 self-driving cars. Any 10-year-old can be told to clear up the dinner table and fill up the dishwasher, and they will do it the first time they are asked. They don't need to learn anything, right? They can just plan that action sequence without learning. 0 shot. Any 17-year-old can learn to drive a car in about 20 hours of practice. Okay? We don't have any of this with AI systems. We don't have robots that can learn to do any of this that quickly. So we're missing something big, it's obvious. And the reason we are missing something big might be because of this simple calculation. Let's take the biggest LLM of today, or some of the biggest LLMs. Let's say Llama 3, right? It's been trained with 20 trillion tokens. A token is kind of like a word. So 2 10 to the 13 words or tokens. A token is typically 3 or 4 bytes. So that's a total of about 6 10 to the 13 bytes for the training data, right? That sounds like an enormous amount of data. It would take any of us here several 100,000 years to read through that, okay? That's an enormous amount of knowledge. And LLMs seem to be able to just, kind of absorb that knowledge, and so we think of them as being smart, but they just have good memory, essentially. Now take a human child, a 4-year-old. A 4-year-old has been awake a total of 16,000 hours. The amount of information that has gotten to the visual cortex of a 4-year-old in 16,000 hours is on the order of 10 to the 14 bytes. And it's because the optic nerve has about 1 million nerve fibers, each of which carries about 1 byte per second. And we have two eyes, okay? So it's about 20 megabytes per second. 2 megabytes per second, okay? do the arithmetics, 16,000 hours, that's about 10 to the 14 bytes. So a 4-year-old child has seen more data, more training data than the biggest LLMs. And that tells you that we're never going to get to human level AI by just training on text. This is just not going to happen. We need to be able to train systems by looking at the world. There's way more information in the real world than there is in text. Text is already kind of a distilled version of reality, and it's too weak, it's too poor. So the next question we need to ask ourselves is, how do we train a world model to make predictions from video? Okay, and of course, and the reason we know that this is important is because we can observe infants, young children learn basic concepts about the world, and we can determine when they learn basic concepts. So things like, object permanence, the fact that, if an object is hidden behind another one, it still exists, right? It didn't just disappear from the world. It's just that you can't see it anymore. That's the notion of object permanence. Babies are not born with it. They learn this in the first couple of months of life. And then to learn about gravity, the fact that when an object is not supported, it falls, this takes about 9 months for most babies. Okay, so we're not born with the notion that the world is three-dimensional. We're not born with the fact that there are animate and inanimate objects. We're not born about the idea of gravity and things like that. We learn this by observing the world, mostly, also by interacting in it. How do we do this? That's what we need to reproduce with machines. Okay, so of course there's a very natural idea, which is to just use the same process that we use for LLMs, using self-supervised learning and training a system to basically predict what's missing in an input, right? So the way you train, so LLMs are a special case of a more general class of models, where the way you train them is you take a piece of text or a sequence of symbols, you remove some pieces of it, okay? And you train a big neural net to predict the parts that are missing. Okay, so this is what's shown at the bottom here. Take a text. This is a piece of text extracted from a large set of news articles. Remove some of the words. Put the corrupted version of the text at the input of a big neural net and train the neural net to predict the words that are missing. This is what LLMs are trained with. It's a special case of that. And it works astonishingly well. Now, here is the thing. If you try to do this with images, it doesn't work. So take an image, corrupt it, and train the image to train a big neural net to restore the image, and try to use the representation that the system learns about images as input to an image recognition system. It doesn't work very well. If you do this with video, it doesn't work at all. So take a video, corrupt it by masking a piece of it, let's say the second half of the video, and then train a big neural net to predict the continuation of the video, and it doesn't work. I mean, it learns something, but the predictions it makes are bad. So here is the kind of prediction you get. This is old work from 2015. Oops, sorry. At the top, you have, oh, you don't see the video, unfortunately. Well, you see it, it's slow. No, you don't really see it. Okay. What you would see is a video that plays, and the little girl kind of gets blurry when the system tries to predict what's going to happen. The picture of the little girl gets really blurry because the system cannot predict what the girl is going to do, whether she's going to move her head forward or backwards or whatever. And so the system predicts the average of all the possible things that can happen, and that's a blurry image. The example at the bottom is a similar one for self-driving cars. Again, the predictions are blurry. And it turns out, you cannot really do video prediction. So if I take a video of this room, I point a camera to the left of the room, and I slowly turn the camera, and I stop in the middle. And then I ask the system, just continue the video. The system, of course, will predict that the camera will probably continue to turn, and it's going to predict that there is another wall in the room, that there are people sitting, and everything. It cannot possibly predict what every one of you looks like. It can't predict what's your age, your hair color or whatever. Hair color, actually, that's pretty predictable here. But hair length or whatever, it cannot predict how big the room is. That's certainly not what's written on the side. So there's a lot of things that are just not predictable in the world. It cannot predict the texture of the wood on the ground. So asking a system to predict every detail at the pixel level in a video is completely intractable. In fact, you can show mathematically that it's intractable because you would have to basically estimate a probability distribution in a high-dimensional continuous space, and that's basically completely intractable. So here's my solution to this problem. It's something I call a joint embedding predictive architecture. And before I explain a little bit what it is, I'm going to show you a simpler example. Okay, on the left, you have a generative architecture. Okay, so a generative architecture, is the one, and it keeps changing on me. Oh, here we go. Okay, there's a delay. So on the left is a generative architecture, okay? It's one in which you have an input, it goes through a neural net, maybe a couple neural nets, and then it tries to reconstruct or predict the output y directly. And the cost function that you're going to use to train the system measures the distance or discrepancy, whatever, between the predicted y and the actual observed y, okay? That's a generative architecture. This is, conceptually, that's what an LLM is. Conceptually, that's what a classification system does, image recognition, they will do this. The joint embedding architecture is the one on the right. So here, the system does not attempt to predict y. It runs both x and y through encoders, and it performs the prediction in the representation produced by the encoders. Okay? So we're not trying to predict y from x. We're trying to predict a representation of y, called sy, from a representation of x, called sx. And what we're going to do is that we're going to train the system all together. Okay? We're going to train the encoder and the predictor simultaneously. There's a big issue with this, which is that the system can collapse. So basically what can happen is that the system can essentially choose to, when you train it to minimize the prediction error, okay, it can choose to just completely ignore x and y, produce constant outputs, sx and xy, and now the prediction problem becomes trivial. That's called a collapse. So we have to find ways to prevent this collapse from happening. But basically, that's the JEPA architecture. This is what I've been working on for several years, what a lot of my colleagues at Meta are working on, at NYU are working on, and a number of people around the world working on this kind of architecture. They're not generative architectures, okay? So everybody is talking about generative AI. What I'm telling you is don't work on generative AI. After telling you don't work on LLM, I tell you don't work on generative AI. Also, I tell you work on energy-based models, which is another way of saying don't work on probabilistic models. Okay, what is the connection with world models? So the connection with world models is that this is basically a world model. Okay? Imagine X is an observation. You run it through an encoder. That's a representation of the current state of the world. The predictor is your world model. The variable A here could be an action that you imagine taking. Okay? And what the predictor predicts is the next state of the world. And when you train the system, you can feed it with what you actually observe taking place, and then train the system to adjust its world model so that you have an action condition world model. Previous state of the world. Okay? Here is the world. Extract a representation of the state of the world. Observe an action being taken. Predict the result. And then observe the result. Encode it in your encoder and compare the representation of the encoded result with the predicted result. And that's how you train your world model. So I told you about this idea of energy-based models already, and the reason why this is the proper way of representing what's going on in the system is because when you train the system, you want to make sure it's not collapsed, and the collapsed model of the type that I explained is one in which this energy surface is flat. It doesn't make any difference between any pair of XY. If you have a system of like a JEPA architecture I just showed you that ignores the input and just produces constant representations, what it means is that it's going to give zero energy to everything. Every pair XY you give it is going to have zero energy. That's not a good model. What you want is your system to have zero energy for training samples, but higher energy for things it's not been trained on. And there's only two ways I know, or two major ways I know, to train systems of this type, energy-based models. Which I should say that probabilistic modeling is a special case of energy-based models, right? What I'm going to say applies to probabilistic models as well. There's only two ways to train them. The first is contrastive methods. So those are methods that consist in generating points outside of the set of observed pairs of X and Y, and then making sure their energy is higher than the energy of observed pairs. Okay, we disconnected again. Non, c'est Zoom. Still connected, but no. Looks like I have no network anymore. Oh, here we go. It works now. Can you put in the number? You put in the number.
c'est toujours sur Zoom là.
Il faut toujours une prise HDMI. Okay, all right, thank you. All right, we're back. Yeah, we can clap to the Wi-Fi gods. Okay, so 2 ways to train an energy-based model, and I'm going to have to accelerate a little bit because we still have a bit of time. And I don't like contrastive methods anymore, even though I contributed to inventing them. And so I'm going to advocate for the other type of method, which are regularized methods. The way regularized methods work is that you put a term in the training criterion in such a way that the amount, the volume of space that can take low energy is minimized. Okay, that sounds a little mysterious, but I'm going to explain how this works. So again, those 2 methods for training energy-based model. One, contrastive, generating new points, contrastive points. And the reason why I don't like this method anymore is that if the representation space is high dimensional, the number of points that you need to generate to take so that the energy surface takes the right shape goes exponentially with the dimension, and so it's not really scalable. The regularization methods, on the other hand, basically attempt to minimize the volume of space that can take low energy, and that works in any dimension, basically. So I prefer those methods. So let me describe a couple of methods that are regularized methods. And the first experiments that were done were several years ago to train joint embedding architectures to recognize images. So what you do is you take an image, you transform it in some way, and you run the original image and the transformed or corrupted version through encoders. And then you train the system to produce the same representation for those 2 images, because you know those 2 images are 2 representations of the same thing, 2 different viewpoints of the same object, for example. If you use a contrastive method, you also have to use pairs of images that you know are different, but otherwise you don't. Once the encoder has been trained, you can use it as an encoder to extract features from images so that you can train, for example, an image classifier or a segmenter or something of that type. And you can train a supervised head on top of it to solve a particular problem. So those contrastive joint embedding methods have been around for a long time, since the early 90s. That's actually a paper of mine. The first 3 papers are from my group, and then there were other work from Google and others around those ideas. You may have heard of CLIP. So CLIP is a joint embedding contrastive system to train joint embedding between images and text. This is what a lot of people like OpenAI use for encoding images, training image encoders. But the type of method I prefer are those regularized methods. And those methods, basically, what they do is they attempt to maximize the information content that comes out of the encoder. So if you have some way of measuring the information content of produced by a neural net, and you have a differentiable way of measuring it so you can maximize it, then you can prevent the collapse. And that's basically a regularizer on the volume of stuff that can take low energy. Okay, so the type of JEPA architectures that we're going to train are of this type, where we have a measure of information coming out of the encoder, and we try to maximize it. Now, it's difficult to maximize information content, because to maximize something, it's good to be able to measure it, or at least to be able to measure a lower bound on it. So you push on the lower bound, and as a result, it pushes on the quantity you want to maximize. Unfortunately, we don't have lower bounds on information content. We only have upper bounds. And so we're going to take an upper bound, we're going to push up on it, and we're going to cross our fingers that the information content is going to follow. And it actually works, okay? Not very well justified mathematically, but it actually works. So one way to do this is through a technique called VICREG, that means variance, invariance, covariance, regularization. It came out a few years ago out of my group at Meta. And it consists in making sure that the variables that come out of the encoder are not collapsed, so their variance or standard deviation is above 1, right? So there's a cost function in the training procedure that says I want the standard deviation of every variable coming out of the encoder to be at least 1. It's a hinge loss. Now the system can still cheat by making all of those variables equal or dependent or correlated. And so you need another criterion to make sure that they are uncorrelated or independent. And you can do this by measuring the covariance matrix of the vectors coming out of the encoder over a batch, and then making sure the off-diagonal terms of that covariance matrix are close to 0. That will decorrelate the variables. And we use tricks to make sure that we also make them independent. This is derived from techniques that people invented many years ago called ICA, independent component analysis. Anyway, this works really well. But that's one class of method. The other class of method is what's called distillation methods, and those ones are a little more mysterious in how they work. They're simpler conceptually, but they are a little strange, and there is a number of different methods like this: Dino, SimSiam, BYOL, IJEPA, VJEPA. They are the ones that people prefer at the moment because they are easy to handle and they seem to work pretty well. And the way this works is that you still have those two encoders, so you have a joint embedding architecture, you still have a predictor. But the weights of the two encoders are shared. So the encoder on the right shares the same weights as the encoder on the left. But in a funny way, it actually uses a sort of a time average of the weights of the encoder on the left, so that its weights don't change as fast, essentially. And there's some theoretical reasons for why this is a good idea. You don't backpropagate gradient to the weights on the right side. And so basically what that looks like is that the network that's on the right side is used to, as a teacher, to train the network on the left side. But they are the same network with some small difference. So it's very strange that it works, but it does work. So this works really well for training a system to extract visual features. There's a technique called Dino V2 or Dino V2, depending on how you want to pronounce it. This is open source and is downloadable. It's probably the best system nowadays where you can just download it and run it on a bunch of images and you get good features. And if you want to do anything with those images, like recognize if there is an object in them or do anything with this is probably the best technique you can use. It was produced by a group at Fair Paris. I'm not going to bore you with details, but I'm just going to give you one example of an application of it. One of our colleagues used the Dino features and applied it to satellite images that were taken all over the world, the entire world. And then for some of those images, we have data as to what the height of the trees is, the height of the canopy, because people have flown airplanes and measured with LiDAR or whatever. So for a tiny part of the world, we know what the height of the canopy is. So what you can do is you train, on top of the Dino feature, you train a small head to estimate the height of the canopy from the satellite image. And then you apply it to the entire world, and you have an estimate of the height of the canopy for the entire world, everywhere in the world, with a resolution of about 1 meter or 2. And that gives you an idea of how much carbon is captured in vegetation all around the world. And this is a very useful data to have for people interested in climate change. But people use this for biological image analysis, for all kinds of stuff. So let me skip ahead a little bit because I'm already out of time. And there is a version of this that we've used to train a video analysis system called VideoJEPA. It's the same principle. Take a video, corrupt it, and train a network, just one of those joint embedding architectures, to predict the representation of the full video from the representation of the partially corrupted one. And once you train the system, you can use it to recognize actions in the video. I'm not going to bore you with details, but here is one interesting or fun application of it, which is a slightly different system, I have to say, because it's using those Dino features. It's very recently published. It's actually on archive. I thought I'd put the reference here, but it doesn't seem to appear. Anyway, it's you take an image of a plate with a robot arm, and there's a bunch of chips on that plate. And what you'd like to be able to do is move the robot arm so that you put the chip in a particular position on the plate. So you see here at the bottom, the blue chips here are in some sort of random position, and you'd like them to be, nicely all regrouped in a square. And what you want to do is basically control the robot arm so that, it goes down on the table and then pushes the chip so that eventually they kind of regroup as a square. Now, if you have a good mental model of what's going to happen when you push those chips with the tip of the robot arm, then you can plan a sequence of actions to do this. And that's basically what that system does, using a world model that has been trained, using representations that are produced by the Dino V2 feature extractor, and using planning of the type that I was explaining earlier, planning a sequence of actions to minimize a particular objective, which is basically the distance between the target image you want and the image that is predicted. And so when you apply this to various tasks, it does things like this. So this is the system, actually the system in action. Let me show it to you. Some videos. Here is the system in action here. So it's trying to push a T so that it's in a particular location represented on the right, and it succeeds in just a few actions. And this is the one I was telling you about. So let me start this again. I hope you'll be able to see this video. Okay, so you see the blue chips at the top. They're being regrouped. You don't see the action of the arm because the action is that it goes on the plate, it moves, and then it lifts, and you don't see the action being taken, but you see the result of it. And so on top is what actually occurs after the system has planned the sequence of actions and executed it. Okay, so it's not exactly a square, but it's pretty close. And what you see at the bottom is the actual prediction that the system made in its own mind. So we run those predictions through a decoder to represent them as an image. And this is what it thinks is happening. Okay, let me play this again. So the bottom is what it thinks is happening. The top is what is actually happening. Okay, and it's trying to push them into a little square. Now, this is a dynamical system that's really complicated to model. And you wouldn't be able to do it with sort of classical optimal control techniques. But the world model basically learned the complex dynamics of what's going on here. Okay, so I'm telling you a number of recommendations here. Abandon generative models in favor of those joint embedding architectures. Abandon probabilistic models in favor of energy-based models. Abandon contrastive methods in favor of regularized methods. Abandon reinforcement learning, but I've been saying this for 10 years already. And at least if you are interested in human-level AI, that's really what you should do. And so these are the 4 most popular techniques, the pillars of machine learning at the moment. And so I'm not very popular when I say this, but that's my recommendation. There's a lot of problems to solve to really get to human-level AI using those techniques. This is not going to be solved next year. It may take 5-10 years, may take longer because we may encounter unforeseen problems that turn out to be much more difficult than we thought. So it may take a while. And I'm not going to go through the laundry list of what problems to solve, but I'm going to tell you one thing, and I think that's very important for Vietnam, which is that we need to do research in an open fashion. This is a university. In a university, we do open research. We publish the research we do. Sometimes people in the industry tend to be a little more secretive. At FAIR, at Meta, we tend to do research in the open as well. We publish everything we do. We publish a lot of our code in open source. How many of you here has been working on machine learning? Okay. How many of you has trained a neural net? Okay, even for a class, right? Hey, don't be shy. Come on. I'm sure there's a bunch of you. All right. Among you, how many of you has used PyTorch? Everyone. Okay. There's more people using PyTorch than people who have trained neural nets. That doesn't work. Okay. Okay, so I don't have my slide, but it doesn't matter anymore because I don't need them. Okay, so we need to be able to publish our research, publish our code. I don't need this slide anymore. I'm good. And here is the future of AI. The future of AI is as I said earlier at the beginning of the talk, we're going to be running around with AI assistants that are going to be with us at all times, perhaps living in our smart glasses. Okay, AI is going to constitute the repository of all human knowledge. And if that's the case, we need AI systems to be trained on all the world culture and languages. If you take most LLMs today and you just use them, they don't speak Vietnamese very well. They're not being trained on a lot of Vietnamese data. Why? It's because it's hard to get. It's only in Vietnam that you can get high quality Vietnamese data. And so the way the future should work is that those frontier models, those foundation models, should not be trained by a single entity like OpenAI or Microsoft or Google or whatever. It should be trained in a distributed fashion by a lot of different entities across the world, each of which has access to their own data, their own culture. How do we get, I was in India a couple of months ago, how do we get LLMs to speak all the 700 dialects that are spoken in India, right? It's not going to be done out of Silicon Valley. So we need some sort of global partnership. It could be private, it could be public, it could be a combination of things, so that we train the big AI system that is going to constitute the repository of all human knowledge. And obviously Vietnam has a big role to play there. But for that to exist, open source AI must be allowed to exist, which means governments should not make regulations that make it difficult or illegal. Thank you very much.
Okay. Thank you so much for your inspiring lecture. As now we will have panel discussion just after, so we will have the time for only one question before the panel discussion. Okay, so please.
Hi. Hello. Okay. Firstly, I would like to send my warmest gratitude for you being here and sharing such a really good presentation. My question is, we are researchers in mostly NLP, in AI for Vietnamese. So there is one problem with working with such problems in Vietnamese, that is the data is quite low resource. And we are working on speech and text mostly, which are quite language specific, as I believe. So we mostly use the multilingual open source data sets models to distill and fine tune to somehow improve the performance of Vietnamese. So do you have any advices for working with low resource problems like that?
Yeah, so I mean, the issue is if you have a small amount of data, the solution to that problem, the universal solution to that problem is self-supervised learning, okay? But the question is, in your particular case, you know, how do you apply it? Now, let me tell you a story. It used to be at Meta for Facebook, Instagram, and the various services doing content moderation in all the languages in the world was very, very difficult. Because it was very difficult to detect violent speech, for example, in every language in the world. It was easy enough to do in English and various other languages for which there is lots of data. But for many languages, including Vietnamese, Burmese, all kinds of languages, it was very difficult to do. And as a result, some people were using Facebook and various other platforms to incite violence against each other. And there was no way it could be detected because we just didn't have the technology to do this. Now, what has changed since basically 2018 or so is now we have large multilingual systems that are trained in a self-supervised fashion. They can do not only natural language understanding from text, but they can also do optical character recognition in multiple languages and multiple scripts. And they can also do speech recognition in multiple languages. So now we have speech recognition and translation systems that can identify 4,000 languages from spoken language. They can translate roughly 1,000 languages in any direction. Okay, and that's an astonishing piece of technology. I mean, the fact that this is possible is really incredible, right? And what we see is that the more languages that we add to the system, the better it becomes at each individual language, right? I'm sure you've seen this. That's why you're using those pre-trained multilingual models. So I'm not saying this is a solved problem, but I think this is a problem whose complexity is going to diminish as those systems become more and more trained with more and more diverse linguistic data. That's another reason for this distributed form of training that I was advocating for initially earlier.
Thank you so much.
Okay, thank you. Okay, thank you. Now we will move forward to the other discussion. So. Okay, so now joining Professor. We are delighted to have two distinguished experts with us. So first, Professor Ho Tu Bao, Director of the Data Science Lab at Vietnam Institute for Advanced Study in Mathematics. So he is a Professor Emeritus of Japan Advanced Institute of Science and Technology in Japan, where he was a professor and head of machine learning and data mining lab in the period 1993-2018. He was also a researcher at Institute of Information Technology of Vietnam Academy of Science and Technology in 1979 to 2010. Also serves as scientific director of Jean von Neumann Institute, Vietnam National University in Ho Chi Minh City. He was also scientific director of the International Research Center for AI of Hanoi University of Science and Technology, and scientific advisor of VNU International School and of Vietnam-Japan Institute for Human Resources Development, a part of the Foreign Trade University. The Professor Bao received a technical bachelor degree in applied mathematics from Hanoi University of Science and Technology in 1978. Master and PhD degrees in computer science from Pierre and Marie Curie University, Paris, in 1984 and 1987. He was awarded the habilitation à diriger des recherches from Paris Dauphine University in 1998. His main research is on machine learning, focusing on development of algorithm and application of machine learning, especially medicine. His interests also include digital transformation, mathematics, and AI for other fields, in particular education and business. So, welcome to Professor Bao. Our second invited panelist is a young AI expert from industry, Dr. Nguyễn Xuân Phong, Chief AI Officer at FPT Software. Please. Dr. Phong has been instrumental in shaping the company's AI strategy. In 2023, he led FPT's partnership with Landing AI, bringing AI expert Andrew Ang on board for APT's K-12 program. Under his leadership, APT became one of 50 founding members of the AI Alliance alongside Meta and IBM. Recognized among the top 150 AI executives by Constellation, Dr. Fong holds advanced degrees from Carnegie Mellon University and the University of Tokyo, with research things at Hitachi and Mila. So please join me to welcome all our guests. Okay, so thank you once again for accepting our invitation to join this panel discussion. So it is truly an extraordinary opportunity that we have Professor LeCun here with us today. So I will make sure to involve you in as many as questions as possible. So, you know, we have received about 150 questions from registered participants, attendees, but okay, so I don't bring all of them here. Okay, so for this discussion, I propose focusing on three main subjects. The first is a topic of great interest to our students from VNU University of Science, as well as many other universities who are attending this event. So this is the path to a career in AI. The second topic covers general questions on the evaluation of AI. And finally, the third subject is on the development of AI for Vietnam, a developing country. So for the first part, so I try to be with Yann. So to start the discussion, could you please share with our audience some personal experiences regarding your studies and career, and how did you get to where you are today? Thank you.
Okay, the story of my life, that's what you want. So I was always interested in the question of like how human intelligence appeared and what intelligence was, and I was fascinated by the idea that machines could become intelligent. I was born in 1960, so AI was, you know, when I was growing up, was very primitive, and I was kind of to some extent disappointed when I learned what it actually was. But I studied electrical engineering. I didn't go to one of the top 3 or 4 schools you might have heard from France. I went to, you know, regular engineering school, if you want. But I discovered really a passion for research, and stumbled by accident on a book that was a debate between the linguist Noam Chomsky and the cognitive scientist Jean Piaget, and they were debating whether language is innate or whether it's learned. And they brought people to argue for their side and everything. And there was one article written by a gentleman who was describing the perceptron, which is one of the early model of machine learning from the 50s. The book the debate had taken place in 1979, and the book came out in 1980 or something like this. So I was in college, or I was in second or third year of college. And I discovered that people had worked on the idea that machines could learn. I found that absolutely fascinating. So I started digging the literature of about that, and discovered that most of it had been written in the 50s and 60s and stopped in the late 60s. People, you know, stopped really working on neural nets in the 60s because of a book called Perceptron that was written by 2 MIT professors. And they showed that perceptrons were very limited, and they basically killed the field more or less. Or what happened is that the field changed name. It became called statistical pattern recognition. You know something about this because you studied with Jean-Claude Simon like I did. So this was a bit of a letdown because I really wanted to work on this topic and nobody was working on it anymore in the early 80s. Now here is something interesting connected with Vietnam. Not a good story, I'm afraid. The person who wrote this book is Seymour Papert, together with Marvin Minsky. Seymour Papert visited Vietnam many years ago, and he was hit on the street by a scooter and fell into a coma and never recovered, basically. He still lived for a few years, but he never recovered his mind. And so he was one of my intellectual heroes. Interestingly enough, the person who took care of him after the accident and tried to make sure he was okay and contacted the family and repatriated him to the US and everything, now works for Meta in Vietnam. It's a small world.
Okay, maybe you can say a little bit about why didn't you come back to France to work after your postdoc?
Okay, so I did all my studies in France. I did a PhD. Nominally, we were in the same university, Pierre and Marie Curie, and I think we graduated the same year. My PhD advisor was not working on neural nets. He had no idea what I was doing. He started working on neural net after I finished because it became kind of a hot topic afterwards. In the meantime, I had met with Jeffrey Hinton and a few other people, and Jeffrey Hinton invited me to be a postdoc in his lab at University of Toronto in 1987. So I went to Toronto. Then I was recruited by Bell Labs. I'd met, so Bell Labs was the research lab of a large American company called AT&T, which at the time was the biggest telephone company. Not anymore, but at the time certainly was. And Bell Labs was a mythical place where a lot of the technologies of the modern world were invented. This is where the transistor was invented, where the solar cells were invented, and where CCD cameras, and there's like 10 of my colleagues were Nobel Prize winners at Bell Labs. So I was recruited by Bell Labs. I could not refuse an offer from Bell Labs. I went there with the idea of staying 2 years. But in fact, I stayed much longer than that. After I left AT&T in 2002, after a dozen years at AT&T, I left. I became a professor at NYU. And then after 10 years of that, I was recruited by Mark Zuckerberg to start the AI research lab at Facebook at the time. And it was really clear after just a couple of years that we needed to open a lab outside of the US, in Europe. Our original idea was to open a lab in London. There's kind of a bias from the US to open lab in London because everybody speaks English. But in fact, it turned out to be a much better idea to open that lab in Paris because there was a much bigger concentration of available talents for AI research in Paris than there was in London. There's a lot of people in London, but they were all already working for DeepMind or Microsoft or some other place. So it was much better in Paris. So we opened this lab in Paris, and it's been a runaway success. And as a result, I've been kind of spending more and more time in Paris because I work with students in Paris. So if you can actually do a PhD advised by me either at NYU or at FAIR in Paris.
Okay, thank you. So we move to just another question for this part of the study. So this question is from some math students at our faculty. The question is, in today's world development, many students are pursuing careers in IT or AI. So is there a path for students majoring in mathematics to have an advantage?
Okay, I'm going to make a very controversial statement. So first of all, I'm not a real computer scientist. Okay, I studied electrical engineering as an undergrad. And the PhD we did, I don't know how to call it. It wouldn't qualify as computer science. I don't know what to call it. It was AI. But it was not computer science. Like, we never learned the core of what at least American universities, consider computer science, like, algorithm and complexity theory and stuff like that. I never learned any of that. Right? So I'm not a computer scientist. But what you learn when you go through engineering disciplines or through mathematics or through physics is that you learn the basic methods that are necessary for things like machine learning. The mathematics of machine learning is continuous mathematics. It's not the kind of mathematics that you typically learn when you go through a traditional computer science curriculum. You don't do enough math if you just do computer science. You don't do enough continuous math. You may never hear what a gradient is. You may never take linear algebra. I don't know what the curriculum is here, but you may never take probability theory. You may never take what Americans called calculus 3, multivariate calculus and things like this. Those are all kinds of things that are really useful. The underlying mathematics of statistical inference in machine learning is the same as in statistical physics, in thermodynamics. It's the same mathematics. So if you learn that in physics, you're better prepared if you study physics or electrical engineering to do machine learning than if you do computer science. That said, you can, of course, do machine learning if you study computer science. Just take more math and physics than you should. So if you have the choice between, taking a course in, mobile app programming or something, between that and quantum mechanics, take quantum mechanics. It will be more useful to you if you do machine learning than if you take mobile app development.
Okay, thank you. So due to the limited time that we have, I'd like to move to the second part on the general questions on the evolution of AI. So one of the most prominent topics today is large language models. To start, I would like to ask Professor Bao. Dr. Fong, do you have any question about abandon of LLM?
Before asking the question to Yann, I want to add something. I received a scholarship from France, and we did the same master program in traitement algorithmique de l'information. And then after that, we continue to do doctor course. For Yann, I very admire him because he continued to work in a problem that at that moment, as he said, not many people pursued. And I go to something hot trend at that time, like deep learning right now is expert system to build an inference engine. Luckily, after 1 year, my supervisor moved to Montpellier, and I changed to machine learning and continued until now. Okay, and then about the question, as I understand, you distinguish human level AI and somewhat like AI assistant. And you say that if you're interested in human level AI, do not work on LLM. Okay. And then I heard that, I see that you say large language model is a good, work well for text, for discrete modality, but not good for something called sensory input. So, but right now, large language model become very popular in AI and make AI come to everybody. So my question is, what is the chance that the LML can extend or evolve to deal with the world problem, or we need some other alternative way as you do? Use self-supervised learning, for example. And when could happen the breakthrough of self-supervised learning to make an alternative to AI?
Okay, so the first point is that LLMs really do not work when you try to apply them to images or video. The only way that current chatbots can handle images is because the image encoder has been trained separately, right? So people have attempted, including some of my colleagues at Meta, have attempted basically to turn images or video into tokens, like you would do text, right? So break up an image into little squares and then turn each square into a vector, and then feed this to an LLM as if it was the token from a text. And this works, but with very limited capabilities. So the way things are handled at the moment is that if you want a chatbot to handle images or video, you train a separate image encoder, right? So OpenAI uses methods like CLIP. At Meta, we use a variety of methods to train those things, including the Dino and things like that. But it's a separate process, right? So it's not part of the LLM. It's just kind of a thing that you add to it. Same thing, if you want an LLM to have some level of memory, you use a technique called RAG, Retrieval Augmented Generation. Okay, it's another thing that you bolt on top of the LLM to basically plug a deficiency of it. And then if you want the system to be able to reason, you do what OpenAI has done with O1, which is that you have your LLM produce lots and lots of different outputs by basically increasing the temperature of the generation. And then you have yet another neural net that picks which of those answers is the best one, which is an extremely inefficient way of doing reasoning. And so all of those things are basically just band-aids, right? They're ways to push LLM to do things that they really cannot do. And it's saturating. What you see at the moment is that the performance of the current paradigm is saturating, right? Why is it that we haven't seen GPT-5? GPT-4 has been out for a long time, and we haven't seen GPT-5. And the reason is, they've tried to train it, and it doesn't work much better. It's the same performance. We're running out of data. We're running out of compute. We're running out of time to fine-tune those systems because we don't have enough people to just teach those systems to behave properly. They still hallucinate. They still don't understand the physical world. They still don't have common sense. The current paradigm is saturating. It doesn't mean it's not useful. There's a lot of practical applications of LLMs. If you are interested in doing a startup or working in industry, you're going to be working with LLMs. LLMs are going to be useful to you. There's no question about it. But if you want to make progress towards more intelligent systems, we have to find a new paradigm. So as I explained, the generative architecture is not appropriate for continuous modalities. You have to use those JEPAs. And conceptually, actually, a JEPA is not that different from a prediction system, except that the prediction, instead of taking place in token space, takes place in representation space. That's the only difference. Now, I've kind of plotted that path to where I think research should go in AI. Not everybody needs to believe this. People who are interested in short-term applications should probably ignore what I'm saying for now. Okay, but if you are interested in research, if you are interested in how AI is going to change over the next 5 or 10 years, this is probably the way it's going to change. What that means is that there's going to be a huge amount of progress in AI systems 5, 10 years from now, or maybe a little less if we're lucky. And my prediction is that, 5 to 10 years from now, nobody in their right mind would still use LLMs.
For me, in working in both industry and academia, and I also work with Joshua Banjo and Mila for quite some times, and we have been investigating like system 2 and reasoning through a lot of different motors, like from energy-based motor to physics-informed motors and so on. So essentially, I agree with you on 2 points. The first thing is the current architecture. Yes, they maybe not evaluated in the right kind of metrics, and also there's a need of higher architecture for objective driven. To reach to another level of reasoning and so on, but that's a how. But we should agree that the what is the current method of generative AI. It is useful with some limited capability. It is useful to solve some of the tasks, and it is useful to contribute at least to our economy and society at the moment, and that I think we depends on what you really want to go in the future. And I agree that if we want to reach human level AI, then a different approach might be a good idea. And LM would be still useful if you go for engineering, if you go for what can be useful, and that Meta has been one of the company that have been supporting a lot of open source development, and they published Llama 3, Llama 3.1, and now Llama 3.2, and that can be useful for many parts of the world. You imagine like education, right? If you bring those models with you say like it's very good at retrieving information, and education is about retrieving information and bring it to another part of the world where like Vietnam we benefit so much from it. We can use it for education. In fact, FPT using Llama 3.1 models from Meta and fine-tune it to become one of the most useful models for semiconductor specific domain, semiconductor domain, and it can be used to teach engineers to learn more about semiconductor, design semiconductor better. So I think that's just you should understand about the viewpoint about science versus application and engineering. Yeah.
One more. How do you think about the trend of specialized ML?
Yeah, I mean, we agree, right? It depends what your horizon is, right? But the reason I'm making this point here is that we have a bunch of young students here, many of them interested in research. We have academics who are interested in research. Perhaps some of them interested in theoretical questions surrounding this. So this is the place to talk about the long-term, long horizon. But of course, if you are interested in short-term applications, obviously you should use LLMs, among other things, right? Yeah, and your question was on specialized. Yeah, so right. So one of the things that we're finding is that in a lot of applications, there's two phenomena that are kind of work against each other. The first one is the one I was mentioning for the question that was asked earlier, the fact that the more data you train a system with, the more it absorbs sort of general knowledge, and the easier it is for it to, basically absorb new things, right? So a multilingual speech recognition system becomes better at individual languages. The more languages you train it on, the better it becomes at each language, which is very interesting. So there is that phenomenon. And then on the other side, there is also the phenomenon that very often for a vertical application of AI, of LLMs in particular, the performance of a small fine-tuned system is almost always better than the performance of a generic large model. Okay? So you're better off taking, Llama 3.2, 3 billion, or whatever it is, so 7 billion, or even the 1 billion, because there is one now, and fine-tune it for your application. It will run quickly, cheaply. It might run on your phone even. And it might be more useful and more accurate than if you just use generic, ChatGPT or Gemini and hope that it will work for your application. You're better off specializing just for cost reasons.
Okay.
I have really quick questions. Yeah. So maybe we can move to the third one after this. So you talk about like the future of AI, and specialized motor and so on. But my question is about like what you see, the reasoning system of LLM in the next couple of years. Is this going to get better from this? Because you already believe that it's already saturated, and is there any other way to make it more useful in terms of reasoning and
So reasoning is search. Okay, I sort of made that point during my talk, but the way you get a system to reason is you have it search for among a set of possible solutions. You have it search for a solution that matches a particular criterion, right? That's how reasoning works. Like every type of reasoning, in fact, every type of computation can be reduced to this problem of search. In fact, early pioneers of AI thought all of AI was just search. The first program that Newell and Simon worked in the 1950s was called the general problem solver. And what it was just, okay, if you can specify a problem space, a space of potential solutions, and then you have a way of measuring the quality of a solution, what you can just do is search through that space for a solution that, optimizes your objective, like, the traveling salesman problem, for example, right? I give you a set of cities and I ask you what's the shortest circuit between all of those cities. I can search exhaustively through all possible permutations and then get the best. Now, what they didn't realize at the time is that almost all the interesting problems are NP-hard or NP-complete, so that's not a good approach. But basically, all of AI was reduced to search, right? And we've completely forgotten that. So what are people doing now, right? So systems like O1 or Strawberry, right? The OpenAI version version of GPT that does some level of reasoning. It does search, but it does search in token space. So the problem with token space is that token space is discrete, right? You can generate, I don't know, there's 100,000 possible tokens in any typical language. So the first token can be one of 100,000. Of course, you're not going to generate all 100,000 because you have a distribution that allows you to generate maybe 10, right? So generate 10. Then for the second one, you have 10 times 10, and then 10 times 10 times 10, right? And that goes exponentially. So you need a way to prune that tree so that you don't generate completely nonsensical sequences of tokens. So you need to train another neural net to tell you which part of that tree are interested to generate. And then you need to have a third neural net that tells you, among all of those, which one actually is a good solution. And that's just ridiculously expensive because it's combinatorial search, which is why O1 is really not practical as a product because it's just too expensive, right? I mean, the amount of time it has to spend to do reasoning is just insane. So a much better approach would be to do this reasoning in continuous space. So instead of doing it in token space, do it in abstract representation space, in embedding space, where it's continuous. If your cost function and your one model and your entire model is differentiable, then you can use gradient-based methods for optimization, and that's way more efficient than combinatorial search. So that's a solution. That's what I'm advocating. Now, we haven't made this work completely yet, but that's where I think the solution obviously has to be there.
Okay, so now another question on the hardware development. So I leave the question to to Professor Chen Xuan-Tu.
So my name is Xuan Tu Chen from Vietnam National University, Hanoi. I got my PhD from France at Gelati and IENPG. So thank you very much for your interesting presentation. I would like to ask a question about the hardware and software development of AI. So as you have diploma from WB and also from CS. So what about your opinion and suggestion for the trend for developing hardware accelerator for AI in the future?
Yeah, so I mean, hardware, specialized hardware for AI is certainly something that during most of my career I was dreaming of and really didn't have access to. When I joined a group at Bell Labs in 1988, that group was actually working on neural net chips. And I participated in the design of some neural net chips. Some of them were actually mixed analog digital mode, so they were doing some of the computation in analog. And this actually, at the time, worked pretty well. But this whole thing was kind of abandoned because neural net fell out of favor. So, you know, what's happened in the last dozen years with the emergence of general purpose GPUs and the fact that basically what you need for training neural net is just fast numerical computation has really been an interesting phenomenon. I gave a keynote at ISSCC, which is the big chip conference several years ago, where I told people, this was before transformers, right? And I told hardware people, look, there is only a small number of operations that you have to implement efficiently, but the main issue is going to be bandwidth to the memory, and the fact that future neural net architectures are going to be dynamical. They're not going to be like fixed architecture. And really what transformers have shown is that, I mean, what a transformer is really is a way of dynamically rewriting the connections in a neural net. When you can try to abstract what's going on, that's really what they do. They sort of dynamically create and suppress connection on a data dependent way. Now, what the hardware industry has focused on is reduce all of those operations to essentially matrix multiplication. And I'm a little disappointed by this because that's only efficient if you process multiple inputs at the same time. If you want to do like real-time streaming, like video analysis or something like this, you can't use the GPUs are not appropriate for this because you can't parallelize enough if you're streaming. So I think there is still a lot of work to do in sort of innovative architectures for that. And then there's a question I get very often, which is there going to be like some major so before I say that, one good thing that has happened is before people have realized that you don't need high precision arithmetics to do the calculation, the computation for neural nets. Sometimes you can reduce it after training to just a few bits per weight and per activation. And some people are working on really exotic representations of numbers for being able to do this really efficiently. So I think you're going to see really low-cost chips that can implement fairly complex neural nets. They're going to cost nothing, and they're going to run in your automated vacuum cleaner and lawnmower and things like that. Right? It's going to be in every toy and everything in a few years. But one question I get very often is there going to be like a completely new way of designing chips that is going to make neural net computation more efficient? Analog, spike-based, things like that. I'm very skeptical. I've worked on analog hardware, and I'm still very skeptical. I don't see that happening unless there is some major progress in device. New devices, right? There was a big hoopla about 10 years ago on memory stirrers, for example. That's kind of died a little bit. It just didn't fulfill the hopes that people thought. This was going to be, programmable resistors, so you can basically run neural nets in analog. So I'm still very skeptical. Like maybe someone will invent some exotic technology with, I don't know, magnetic domains or carbon nanotubes or something like this, but right now I don't see it, right? And every 5 years or so you see someone claiming that optical implementations are the best thing, and they create a startup, and then 2 years later it dies because they can't deliver. So,
I think for now, most of the architecture can be optimized for some certain task. Like the transformer architecture, it can be optimized to run on some hardware. But a general one, like if you apply, a general neural networks, like even ConvNet and everything, then there's I believe so. It's very skeptical to have a general architecture for neural net. But so maybe the next one will be quantum computing. I don't know.
So actually, I think convolutional nets are much easier to optimize than transformers. Transformers are really horrible because you need global connections, so you need long range I mean, you need to shuffle a lot of data. You need to do, n-squared computations. Convolutional nets are super efficient in terms of memory bandwidth. And so I don't see this, so there's something very interesting. When you see academic papers on computer vision, many of them use transformers, okay? But when you see the practical deployed applications of real-time computer vision systems, they all use convolutional nets. Not a single one uses transformers. It's just not efficient enough, right? So that tells you something about the discrepancy between, the sort of research academic world on one side, and then the practicality of actually running things in real time. Your car, your driving assistance system on the highway, it's a convolutional net. It's not a transformer.
Okay. This is so interesting. So we are running out of time, so I try to keep just one last question. Because there's a lot of lecturers, teachers who follow these discussions. So the question is, how is AI used in education? How will AI development reshape education? What is the role of teachers in the AI area? I don't know, Professor Bao, maybe you want to say something?
Thank you. So we go back to AI and education. So maybe, Yann, just to say, with generative AI, most people in Vietnam know about AI. And many people, it makes access to most people. Before, very few, not many people can use AI, just run the predictive AI. But after that, everybody talking about the generative AI, Gen AI. So I think it has a big impact to education. And the context of education in Vietnam is very different from other countries, from France or from America. So our country is very long and many mountain area with very imbalanced in education context for different group of people. And totally, I just checked last night, we have so far, by the number of Ministry of Education in last September, we have about 22.7 thousand students, of that 2 million university students, and about 1.7 million teacher, a huge number, but very diverse. So people talk much about the impact of AI in education, but in my view, in my vision, situation in Vietnam is somewhat different from other places. And I think, firstly, AI like Gen AI even is not the one way safe to use, but could be a very good tool for, firstly, teacher. Our teacher can improve their knowledge and connect their activity to the source, the knowledge source around the world. And that's something I see we lack. And of course, secondly, I think university students who start to learn some profession, their career, and they also can use the tool of AI to improve their study. And for high school, even smaller students in high school, I think we don't need to be very hurry, because Gen AI also as AI is continue to change. And maybe just in a few years, we can see everything more clearly. But anyway, I think AI is last few years can play a role to reshape education in Vietnam, particularly when you have, in general, more difficulties in other places around the world in our context. So I think really it could play a very important role to improve the quality of education. Particularly, I think first go to the teacher. We have around 1.7 million teachers. And just imagine if all teacher can use in the right way Gen AI and as a tool, they certainly can improve their education teaching.
Yeah, I think there's no question that AI is going to help disseminate knowledge in various ways, and so help with education or access to education, certainly. I mean, this is to some extent what every communication technology ever invented has really allowed. If you think about, in the past, another technology that had a similar effect that AI may have in the future, giving access to knowledge and information, the only equivalent I think we can find, maybe besides the internet or something like this, would be the printing press. The invention of the printing press in the 15th century has allowed the dissemination of knowledge, has, at least in Europe, has brought about the century of the Enlightenment. Philosophy, science, rationalism, etc. It brought down the entire political system in Europe, right? And basically enabled things like the French and American revolutions, right? And the emergence of Western democracy, for example. So there's been like a huge effect just because of the printing press, that it's dissemination of ideas. Now compare this with what happened in the Middle East. So in the Arab world, the Ottoman Empire actually banned the printing press. It banned the use of the printing press for Arabic. It was okay to disseminate books in other languages, but not in Arabic. And the reason was multiple. The first one was to control the dogma, religious dogma and political control, of course. But one big reason was to protect a corporation, to protect the corporation of scribes. Scribes were very powerful people. They were the people who were writing Arabics, and of course their profession would have disappeared with the printing press. And so to protect them, because they were powerful, the sheikh essentially banned the printing press. According to some people I've talked to in the Middle East, the Minister of AI of the UAE, for example, this is one of the major factors that caused the decline of the Ottoman Empire and the Arab world, which in the Middle Ages was dominating science in that part of the world. So there's a big lesson here, which is that you have to embrace communication technology when it gives people access to knowledge. And if you limit access to it, you run the risk of just falling behind. And some countries are making that mistake. And it's a very bad mistake to make. So certainly AI is going to help with disseminating knowledge and is going to help with education. In the shorter term, AI is an incredibly efficient information retrieval tool. And so it's very difficult now to design an exam for college students whose answer cannot just be found by asking a question to a chatbot. Okay, so it becomes more difficult to test students. Basically, what we have to do, and as professors, it's a difficult thing to do. We now have to figure out how to ask questions to students that require them to understand the topic, not just regurgitate it. Okay, and so the whole idea that we learn things by rote and we can just regurgitate it is dead. We can do this with LLMs now. We have to use our brains now. We have to use our brains for what it's good at, which is really sort of deeply understanding the world. And we don't know how to test for that. We don't know how to educate people for that. It's a challenge.
And I think one more big thing is AI will help to overcome the obstacle of language. I think most teachers now can read every document in English, French, Spanish, German, etc. So I think that's also very important for our education.
Okay, so I'd like to continue the discussion all the day, but now we should close a panel discussion here. So thank you very much, Professor LeCun. Thank you very much, Professor Otubao, and thank you very much, Dr. Nguyễn Xuân Phong. So thank you, everyone. Thank you.
So Dear honor guests, the lecture of Professor LeCun on the future of AI and subsequent panel discussion were really interesting and attracting not only for the audience in this auditorium, but also for those watching on live via Facebook through our live stream program. The speaker has shared profound insight and multi-faceted perspective on the future of AI. Thank you for all your contribution to this event. So hereafter, I would like to invite, sorry, just, okay, now before we coming to the section of the gift, so yeah, we will take the photograph group, okay. Okay, thank you. So now I would like to invite Professor Vũ Hoàng Linh to give the to present the gift for on behalf of VNU University of Science to invited guests. So please. So the vâng, mời các bạn sinh viên lên chụp ảnh cùng cả. Vâng. Okay, we one more. Vâng. Xin mời các bạn. Xin mời các bạn. Vâng. Vâng, xin mời các bạn sinh viên lên chụp cùng ông ạ. Vâng.